Hello everyone and welcome to another energy problem solution video. This is for energy problem set number 2, and I'm just going to go through these quickly. I'm probably not going to go all the way to plugging the numbers in because I trust everyone here knows how to use a calculator. I'm just going to get to the point where the equation is all set up and you just have to plug things in to get the answer. So here we go. A car, 1250 kilograms, is waiting at a stoplight at the bottom of a hill. When the light turns green, it quickly climbs the hill. At the top of the hill, which is 30 meters high, comma, the car is traveling at 10 meters per second at the top of the hill. We draw a sketch of the situation. This is important. So we've got the hill, our car. We know that the hill is 30 meters high, and we know that the car at the top, so this is before is down here, and then after is up here where it is at the top of the hill and traveling at 10 meters per second. Okay, I'm going to set our zero reference point to be the bottom of the hill. That's important. And of course our system, which I'll put up here, is going to be the car, the earth, and that's it. So draw a sketch of the situation. We have to now draw a bar chart. So I'm just going to include gravitational, potential, and kinetic in this one. You could keep writing all the other types of energy that can exist, but just to be quick about it, I'm just going to do these two. Alright, so at the bottom of the hill, where it is waiting at a stoplight, so we are assuming it's not moving, at the bottom of the hill. And when it's done, it quickly climbs to the top of the hill, right? So it starts off with no energy because it's not moving, v equals 0, and it's at the 0 reference point, so gravitational potential energy is equal to 0. And then at the top, it ends up with some amount of gravitational potential energy and some kinetic energy. It might not be the same, I don't know. Here, let's do this just to differentiate. So that means that for the car to have no energy and then gone to the top of the hill, some amount of work has to have been done on it. And the question is, what did this work? Part C, right? So this is part B. Part C is asking, is there work done on the car? If so, what object did the work? Now, most people, their first instinct would be to say that the engine did the work, but if you recall, the car and the engine is in the car, is in the system. So obviously the car cannot do work on itself. What actually does work is the hill, or the surface of the hill that helps to exerts a force to push the car up. Even though it is technically the car pushing on the ground, due to Newton's third law, the ground pushes back up on the car to bring it to, and do work up the hill. So this would be the hill, or the ground, whatever you want to call it. Alright, D. If the car goes from the bottom of the hill to the top of the hill in 30 seconds, what was the power of the car? So we know that power, that's a capital P, not to be confused with momentum, is equal to work over time, right? But we don't know what the work done is, and so you could try and calculate the work that it did to push it up, but the fact that it's moving too means that some work was done to move it forward. So just calculating the work done from force times distance is not going to be the best way to do this one. What we're going to do is we're actually going to use our bar chart that we made, since that's what it's here for, to create our equation to find out what the work is. So if you add this up, you see that the equation we get is work is equal to gravitational final plus kinetic final. And this work is exactly what we need up here to find the power. So I'm going to rewrite this equation as our UG final, which is just mgh plus 1/2 mv squared, and this is all final, right? H final and V final over delta T. So we know m, we know the mass of the car, We know g, 9.8. We know the height, 30 meters. We know the mass again, and we know the final velocity, 10 meters per second. So plugging everything in here with the time will give you the power spent by the car to get to the top of the hill, or the power that the hill spent to get the car up to the top of the hill. Anyway, moving on. So draw 2 different energy bar charts for the following situations. Be sure to list any objects and conditions to consider within your system. So a few people had a problem with this. The bar chart, there have to be 2 separate bar charts for each one, 2 for A, 2 for B. So we'll make these 2 will be for A, these 2 will be for B. I don't know why I made that capital. There we go. So let's start. So a skier is skiing down from the top of the hill initially. She is moving very quickly. Afterwards, at the bottom, she's stopped and notices that her skis have melted some of the snow while she's stopped. Okay. We can look at this in 2 different ways. So in order to make a bar chart for 2 different bar charts, for the same situation, for the same before and after, namely the skier moving very, very quickly at the bottom of the hill and then stopped, you have to pick different systems. That is the only way to get 2 different bar charts. So first let's pick our systems. Let's pick the skier, the earth, and that's it. Just the skier and the earth. What we can do is we can, if our system is the skier and the earth, then we should really only have gravitational and kinetic for this one. I'm going to throw delta U internal in there also. Initially, our skier is moving very quickly from the top, or from somewhere at the top of the hill. So presumably she's going to have a lot of gravitational potential energy and a decent amount of kinetic energy also. She's moving very quickly. At the end, she is stopped and has melted some of the snow. So in this case, since the snow is not in our system, we don't have to worry about the fact that the snow is melted. We don't have to worry about the energy that was moved to the snow because, again, it's not in our system. So at the end, she has no energy if she ends up, right, ZRP is at the bottom of the hill. All right, so no energy, which means that all this energy from here has to have been taken away from the system from work. All right, so that's 6 bars down. That gets rid of all these. And by 6, I mean 7. There you go. Now, what about another situation? So that's the first one. Now, let's pick the system of, we could either do just the skier, or we can do the skier, the earth, and the snow, which does change things a little bit. I'm going to do the latter. Let's do the skier, the earth, and the snow. All right, obviously there's many different ways to do these 2 problems, all depending on your system. So these are not the only 2 right answers. If you did something else, then I'm sure it's fine. You can check with me or Ms. Resnick if you'd like to get assurance if your solution was correct. I'm sure we wouldn't mind telling you. All right, we still start at the top of the hill, so I'm going to start it with the same energy that we had before. Okay, same initial and kinetic energy, initial gravitational and kinetic energy. But this time, because the snow is in our system, it could not do the work to slow us down because it's in the system. So what happened to all this energy? Well, remember at the end here it says, notices that her skis have melted some of the snow while she stopped. Well, the snow melted because some of the energy from this gravitational and kinetic energy is transferred into the snow in the form of heat energy. We'll learn more about that next year if you happen to take AP2. That's one of the first things we're going to learn about. So this is all transferred into heat energy, and since the snow is in the system, we can account for this heating energy by counting it as a bar here. So instead of having this negative bar for work, we're going to have a positive bar here in the internal energy to account for this. And so these are two different bar charts for the same scenario. Now, what you could have done, another thing, is you could have said, all right, let's take the Earth out of the equation and just have the skier in the snow. Then you wouldn't have had any gravitational potential energy, but you would have had the Earth doing, the same amount of work that it would have had the energy if it were in the system. That's another version of it, and you'd still have the same kinetic energy, and you'd still have the same delta U internal. All right, let's move on. Initially, a foam dart is loaded in a Nerf gun with the spring compressed. Somebody fires the gun into the air. Afterwards, the dart is still moving upwards away from the gun. I'm taking this to mean that the initial point is when the gun is loaded, and then the final point is when the dart is not in the gun anymore and it's going up into the air and it is still moving, so it hasn't reached its highest point yet. Let me just fill in the rest of this table. Final, US final. All right. For the first one, I'm going to consider my system to be the Nerf gun, namely the spring in the Nerf gun specifically. The dart and the Earth. Why not? If all of these things are in the system, and I'm going to consider the zero reference point to be the launching point of the dart. Right, so that's the zero reference point, at the launching point of the dart, so that means that there's no gravitational potential energy to start. There's also no kinetic energy to start because it's not moving, but there's a whole load of elastic potential energy because it's loaded against this spring. Then, in the second half, it is going up, speeding upwards. It's not at the zero reference point anymore, and it is moving forward. So now there is no elastic potential energy because the spring is not compressed anymore. And there's going to be some gravitational, not much, I'm going to say, and mostly kinetic because it's speeding upward. In this case, I'm assuming that there's no internal energy, there's no heating going on here, so I'm going to keep that at zero. And because there's no objects external to the system that could be exerting a force on it, assuming no wind resistance, right, assuming no air resistance, I'm sure there could be a little bit of work done by air resistance on this foam dart, but I'm going to assume no air resistance. There you have it. Now, for the second one, there are, like I said before, several different versions of this that you could do. You could do one where it's just the gun and the dart, in which case the Earth would be doing negative work as it was coming out of the gun. You could do the dart and the Earth, which means that there's no energy to start, and then the spring in the gun does an amount of work on the dart equal to this. But what I'm going to do is I'm going to choose the system with just the dart because I want to show you something that is completely possible in a problem like this. So if the system is just the dart, let's just look at the before and after first. Before, if the dart is the only thing in the system has no energy, and then all of a sudden it has 3 bars of energy here. And somewhere this thing got energy from something to get this kinetic energy, right? There's no gravitational, there's no elastic. But there's 2 things now doing work on our system, right? We've got the spring doing work on the system, but we've also got the Earth doing work on the system, right? If we have 2 things exerting forces on our system doing work, then we have to actually have 2 bars in the middle here. One is the work of the spring, and one is the work of the Earth. All right? Now, here we said that the spring initially started with 4 bars of energy, so I'm going to assume that means that the spring can do 4 bars of work on our system. But we also said that it ended up with 1 bar of gravitational, so that means in that same distance, the Earth will have done 1 bar of negative work. This is allowed, okay? I would much rather you drew 2 bars here to show each individual energy versus drawing one bar for work and having a bunch positive and some negative. It's a little confusing. All right, so this is a completely reasonable bar chart for this problem. Like I said, you could have also picked one, I'll draw it in a different color, where you had no gravitational potential energy if it was just the dart and the spring in the system. Then you would have had elastic potential energy and you would have had negative work and the same kinetic energy at the end. Or you could have switched these two around. You could have the Earth in the system but not the spring, and then so you would have the Earth and the dart, which means that you would have no gravitational potential energy to start, obviously, but you would have gravitational potential energy to finish up with, and you would have the spring doing this much work. So yeah, I hope that clears things up. The bar charts are completely based on what you need for the problem and how you pick your system and your zero reference point, obviously. All right, moving on. So, a popular new spring hockey game that Jay got for his birthday uses springs to move a .003 kilogram puck. That's a 3-gram puck for those playing at home. It works like a regular hockey table game, but instead of hitting the puck, the players use small springs. Each spring has 120 Newton per meter spring constant and can be compressed up to 0.02 meters. How fast does the puck move when it departs a spring that was initially compressed this distance? If the spring is able to push the puck away in 0.2 seconds, what is the power generated by the spring? Okay, so this is actually fairly easy. If we consider our situation to be the puck is on the compressed spring. To start, remember it was compressed this distance, 0.02 meters. It is a 3-gram puck. And K, we said, is 120 newtons per meter. Then we can consider this to be the before and the after to be where the spring is now unloaded and the puck is flying off in some direction, right? Some V. And this is what we're looking for. How fast does the puck move when it departs? So this is the question. So I'm going to draw a bar chart for this system, and I'm going to consider the system to be the spring and my puck. So I'm going to just draw a bar chart here really quick. All right, here we have our bar chart. If you look at our system, this is sort of like an above view or even like a side view if this is the ground. But either way, there's no gravitational potential energy before or after. It's a flat table. I'm going to ignore it. I'm going to assume that it starts off with no velocity, obviously, so 0 kinetic energy initial. And then it is a compressed spring. The spring is in the system, so there is an amount of elastic potential energy here. Then if it is like a hockey table, there's, I'm assuming, very low friction, so there's nothing doing work. And it ends up with no elastic potential energy because the spring is no longer loaded, but it has some velocity, so it has some kinetic energy. The same amount as here. So using our bar chart to write out the equation, we get US initial is equal to K final, which means that we got our equations 1/2 K delta X squared is equal to 1/2 mv squared. Solving for V, we can multiply both sides by 2, which cancels out the 1/2. So we get K delta X squared over the mass and the square root. So this is going to give you your final velocity. Then, if the spring is able to push the puck away in 0.2 seconds, what is the power generated by the spring? So, if we look at the work that the spring has done on the system, or the change in energy of the system, then we can find out what the power would have been on the puck. In order to do that, though, we cannot consider the spring to be in the system, because if you recall, the power generated is work over time. The spring cannot do work if it is in the system. So there's two different ways to do this. one way would be to find the force that the spring exerts on the puck over this distance, and then use that to find the work done. The problem with that, though, is that the spring actually does not exert a constant force on the puck. If you remember, the force of a spring on an object, in this case the puck, is going to equal to k delta x, right? And realize that this means that as this delta x changes, so as this decompresses, the force is going to change. So the way we deal with that is, instead of taking the actual force that is exerted, we take the average, or there's a simpler way. If you remember, the work is also can be described as the change in energy, delta U over delta T. And since we know what the final energy of the system is now because we have the velocity, we can just say that the work done on the system was enough to get it to this velocity. So if we consider a system without the spring in it, just the puck, then our bar chart would have nothing here. We'd have the work from the spring, and then we'd have the final kinetic energy. So I'm going to use my final kinetic energy to find the energy of the system, the change in energy, because it went from 0 to some energy here, right? So 1/2 mv squared, that's going to be the amount of work the spring did on the system over delta t, which is 0.2 seconds, right? So this would give you your power as well. Just because the equation says work over change in time does not mean you have to use the equation in force times delta x, okay? There's multiple ways of finding the work done on a system besides this equation. Like, for example, finding the change in energy, all right? Keep that in mind. It'll make your life a lot easier. All right, one last one. So, problem. You are traveling in a 2,000 kilogram Chevy at 20 meters per second going up a hill that is 5 meters high. Suddenly you see a goose crossing the road 20 meters in front of you at the top of the hill. You know from previous experience that when you hit the brakes, a 16,000 Newton friction force opposes your motion while you hit the goose. And so the proposed solution is the one listed there. You'll notice this here, 1/2 times some amount of kilograms, which is mass, and some amount of meters per second, which is velocity. So this is kinetic energy is equal to 16,000 newtons times delta x. This is a force, this is delta x. So what the person has done is essentially set up the bar chart of initial kinetic energy. I'm going to throw this in here just because. So this person has set up a bar chart of, how do I always do that? Of initial kinetic energy and negative work, and set that equal to 0. This is great, except the only amount of work this person considered is the work done by the ground caused by the car braking, right? Trying to stop. What this person forgot to mention, or forgot to take into account, was the fact that the Earth is here too. This thing is going up a hill, right? The idea being, if there is a goose up here somewhere, that ball is a goose. The hill, we said, was 5 meters high. And the car is going up this hill. And the goose is 20 meters in front of him. All right, so we're assuming he gets to the top of the hill before when he hits the goose. So he's got the fact that he's going up a hill means that the Earth is also causing some change in energy, either by doing work or by simply including it in the bar chart if he starts from the bottom of the hill. So that is the first mistake. The first mistake is that there's no UG anywhere, right? Or UG is missing. That is definitely one incorrect thing. So let's fix that. When he gets to the top of the hill, while he is missing the kinetic energy, that's not all of it. Some of it has gone into some gravitational potential energy as well. All right. I'm still stopped at the top of the hill, so now this equation is okay. So we can use this to create our equation. We've got kinetic initial minus work is equal to UG final. So 1/2 mv squared minus the force of friction that's listed up there times delta x, which is the 20 meters, is equal to mgh. This being the height of the hill, this being the mass of the car, this being the mass of the car, this being the initial velocity of the car. And so you would solve for delta x with all this. And what you'll find, actually, if I'm not mistaken, is that the delta x, now that the gravitational potential energy is included, the delta x comes out to be less than 20 meters, and the goose is actually not a goner. And that's it. So from here, you would just plug in, you would solve for delta x, which would look something like this. That's what the final algebraic solution would be. You'd plug in all the numbers from your problem in here, and you'll get, I believe it comes out to 18 meters. I'm about thereabout. And that means that the goose is safe. All right. I hope this was helpful. Good luck studying. Don't forget that the multiple choice questions and the bar chart game are all, with their solutions, their respective solutions, are all in the files section of the SchoolFusion page for your class. That's it. Good luck. See you on Monday.